Okay, and good morning to everyone on a windy Monday morning. And we were listening to what, Debbie? Okay. That was the Rolling Stones again? Okay. Title to be determined later. Okay. We have a quiz that we did on Friday, and I'd like to return that at this point and talk about it and see what should have been done. So I think what I'm going to do is just toss them over this way, and that way they can be returned. I need to get a couple of them recorded here. Let's see if I have any others that need to be returned. I think that's it. And let me just jot down some information here briefly, and I will then get those others back. We were looking at problems from 6.5, 6.7, and we'll talk about them here momentarily. Okay, I'm just going to pass these again your way, Michael, so if we can get those again. And let's look at the problems, what should have been done. This is the first one, which should be déjà vu time. We found the volume. This was of a cylinder. This is what we had done in Math 10. It was part of the homework that you had for the problems we were doing. And I'm trying to figure out how I want to do this. I think maybe I'm going to work with this, strictly speaking, as we come off there with what I have written out. Of course, this is your formula. V equals pi r squared h. And one of the biggest difficulties was remembering the formula. Now the next point is, you'll notice that the diameter is 2.5 inches. So if it's 2.5, what's that as a common fraction? 5 halves. It's an improper fraction, 5 halves. And so what is 5 halves when you divide it by 2? 5/4. Now I rigged these problems, and by the way, the papers are coming back somewhere. Where are the papers? Just pass those up towards here in the front. At this point, I rigged these problems so that maybe with fractions it would have worked out for you reasonably well. And so this was what I did. Made it a heck of a lot easier than what you did. Because the idea is that you had 5/4, so if you squared that, you get 25/16. Okay, and the 16 is going to go into the 32, giving you a 2. Okay, then the 2 canceled with that, giving you a 5. The 5 went in there, giving you a 5, and you had 1570 cubic inches, and you're done. Now, some of you tried that with taking 2.5, getting 1.25, squaring 1.25 as a decimal, and doing everything with decimals. And here was a case where it went so smoothly if you'd have just used fractions. Now, I didn't show what I did here in the sense I did that in my head. You had a 16 down here, and the 16 into 32 went twice. Okay, so the idea was that was straightforward, should not have caused the grief that it did. Any questions there? There's the formula. Pi r squared h. And that was the formula we had for a cylinder in Math 10. And of course, what I've tried to share with you repeatedly, Math 10, I'm holding you accountable for. You must be able to do what we did in Math 10. Okay, the next one I rigged also. Here was the original problem. Let me come off there just a little bit, Debbie. It's a little bit too compact. There's the problem. Now, I did sort of a combination here. 0.45 is 45 over 100, which is 9/20. And then I treated the 5 1/3 as 16 over 3. Then I was able to cancel very nicely and get 3.25 minus 2.4 for a 0.85. Question, Kim?
In the book, it shows 3 different ways to do it, this kind of problem.
Yeah.
And one was to put a 1 under where the decimal is.
Can.
Why is that?
Okay, if we come back and look at the problem, 0.45 is 40. If you're going to have 0.45 over 1, you have to treat it as 45 over 100. Okay? So again, if you have 0.45, you can put it over 1, but you have to change it so you don't have the decimal on the top. So that's 45 over 100. If you leave it as 0.45 over 1, then you change this to 5.33, and some of you got a 0.84999 kind of thing, which I gave you credit for. But the point I've been trying to make is be careful about how you think your way through these problems so that they don't become so convoluted. Okay, let's go to the next one. It's coming off there. This one, let's see, left side as we come to the problem. It's a 2, but you have a plus 0.5x. You have to do the distributive property multiplying through by both. So that's a 2 plus a 0.5x. Here you have your 3x minus 4.25. What I did was add 4.25 to both sides, subtract 0.5x from both sides, and you get 2.5x into 6.25. And I expect you to know that 25 squared is 625, therefore x is 2.5, without even doing a division. Any question there? Okay, coming off there, the Pythagorean theorem. Here's the diagram I gave you. The point is, you square each of these sides. X squared plus 4.5 squared equals 7.5 squared. I gave you 4.5 and 7.5 because there's the shortcut. 7 times 8 is 56.25. 4.5 squared, 4 times 5 is 20.25. Subtract 20.25 from both sides. X squared is 36, so x is 6. Okay, that should have been fairly fast. Then what I wanted and didn't get, but I was a lot more accepting of getting the right answer at this point to get some points out of the quiz. Here was the set, multiples of 3. Here's your outcomes. And the probability of E is 2 out of 6, 1/3. That's what I wanted. Okay? Now, well, if you have 0.333333, no. Probability has to be a fraction. It's going to have to be less than 1, so it'd have to be a 0.3. So, in terms of the problems, the intent was they were all rigged with the idea if you thought your way through them, worked at them, I thought 10 minutes would be more than enough for all those problems. Now, what continues to be the case, on the quizzes, we aren't doing as well as I'm hoping. And we've got an exam coming up. So what I'm going to take time is to put in perspective where we are week 12. So I'm going to come off there. And let me get this set up again so I can move around. Okay, let's cut to the document. Can please, Debbie? Here is week 12. We just finished week 11. We went up through 7-2. Now I need to answer some questions on 7-2. The only thing I did in 7-1 was go ahead and use the probability material. So if we come over there, we go to week 12. This week, I've decided to omit 7-6. I don't like the way that's set up, so we're going to do 3 sections, 7-3, 7-4, 7-5. You're going to find, as we come off there, that 7-3 is just the American system of measure with dimensional analysis. Not a thing new. Everything we did in Math 10 with dimensional analysis. Then we do mess it up a little bit in 7.4. We're going to go to the metric system and see the relationship of meters, centimeters, kilometers, and so on. Then in 7.3, we tie some things together with dimensional analysis, or 7.5, I'm sorry, tie things together with dimensional analysis, and that finishes that chapter. As we come back to the document cam, week 13, that's next week, we have 3 sections, 8, 1, 2, and 3. Those are percent problems. So 8.1, changing from percents to decimals, 8.2, just classic percent problems, and 8.3 ties it together with proportions a little bit. All that we have done in the percent units. So what I'm saying is from here on out, dimensional analysis and percents before the exam, there isn't a single thing that we didn't do in Math 10. And we aren't doing it in any different way. Now, question, how much do you remember of percents from Math 10? How much do you remember about dimensional analysis from Math 10? And I would suggest to you that it's not a bad idea to go back and dig out dimensional analysis and do a few problems, just reminding yourself of how it's done. I'm going to look at that today. But I'd say our biggest problem is in 2 parts right now. One, the recall from Math 10. Secondly, as you're looking at problems, you aren't analyzing them to ask, how could I do it? And you're sort of knee-jerking in a method where I'd say, if anything, you're trying to push decimals too hard, where you can sometimes go to a fraction and make it work a heck of a lot easier for you. So that's where we're headed. Test next week. And what I'd like you to realize as we go back one more time, and that is how close we are to the end. There's the end. Week 15. Okay, so we're in the 12th week, and there's 3 weeks after this, and we're into finals. Okay? So with all that done, I'm going to take some time just to review a dimensional analysis problem that we've done earlier, just to remind you what's done, because that's where we're headed, and I think that might not be a bad way of starting. So with all that done, let's go to a dimensional analysis problem. And I'm going to go back to what we've done before. And I'll just put a typical problem. Using dimensional analysis, okay, this is just a good old problem from the past, and unit factors. A heart patient decides to walk 500 yards each day. Okay, now, if you were here at the college, and you had the stadium right here, and you lived very close to the college, that'd be an easy thing to decide. You just go to the football field and walk from one goal line to the other. There's your 100 yards. Repeat that 5 times. There's your 500 yards. So there's no guesswork in this. It'd be an easy thing to do. And then the question is, how many miles, as we come back, how many miles will he or she walk in 10 days? So when we do this, and the key phrase as we look at this is how many miles? Dimensional analysis. So I'm going to go to the board, Debbie, and we're going to start with some fractions. And usually we don't need very many of them. And what is my agreement for the first fraction? What do I agree to? Whatever I want at the end, I have in the first fraction at the top. So I want miles. Wow. That looks like we're going downhill. Is it that bad in terms of just being level? No, okay, so we're going downhill in miles. Miles downhill. Let's go back to the document cam. We have some information about how many yards this person walks in a day. So what are we going to need in this problem as we go to the board? Miles and what? Yards. Or if I can't remember yards, I could do what? Feet. Handle it that way. So let's say I don't remember anything about yards, but I do remember Mile High Stadium at 5,280 feet. Okay? Now I know something about yards and feet. That 3 feet will equal 1 yard. And now what do I do with the dimensions as I put them down? I cross them out so that I've canceled them. And if I have yards here, remember how this is self-guiding? This must be yards up here. Now I have some information, so we go back to the document can, that it was 500 yards each day. The each translates into 1. So I can go ahead and cancel yards now. And I know that the next one has to be what? Has to be days in the top. Otherwise, I'm not going to be able to cancel these dimensions so that I'm left with the miles I had up here. So, do I have something about this as I go back and look at the problem? You want to know how many miles we'll do in 10 days. So I'll just put the 10 here. Right up there. Isn't it 10 in the problem? Let's go back and look at the problem. It says 10 days. Now the days cancel. Then what was your next step that you were supposed to do? Rewrite it with just the numbers, correct? This is just a review. So I have a 1 and a 3 and a 500 and a 10, and it's over 5280, a 1 and a 1 and a 1. And we have our units at the end. Now, these were rigged many times so that what would happen? You could cancel and make it a little bit easier. Well, let's see what we can do here. Certainly, I can cancel the 10 here and the 10 there. Now, if I add the digits that are remaining here, 15, I can't divide by 3. I'd have to have something that's divisible by... I was thinking it will. I was thinking of 9, and I will with the multiple of 3. So 15 is divisible by 3, giving you 5, so 3 into here, 1. And this is going to be 176. We in agreement with dividing by 3? And then the 500 and this are both even. So 2 will go into there, 250. And 2 will go into here, 88. And then what again? 2 into here for 125 and into here 44. And I think that's all I can do in terms of canceling. So I'm going to take the 44 into 125. Okay. And it's nearly 3. Okay, because if I were to, just as an estimate, if I were to multiply 3 times, I'd have 132, so just under 3 miles. Okay, so this is going to be 2. We have an 88, so I'm going to have a 7 here, a 3 here, a 0, and this is going to go, it looks like, about 8 times, so 2.8 plus miles. Now, that's just sort of a review of the process we went through. This was one of the problems that you did before. Now, I want to contrast that to what we're doing with the same idea. This was the American system with miles, feet, yards. Very comparable. Bomar? More digits to come. The plus sign just means there's more digits to come, so it's more than 2.8. I didn't round off. What I'd like to do now is compare that to a typical problem in your book dealing with section number 7.3. Now, they aren't quite as interesting. Okay, looking at problem 11, 6.5 miles to feet. So 6.5 miles. So you could say how many feet in what? 6.5 miles. But I want this to go to feet. Well, if I want feet at the end, that's where I start. Same idea, it's just a heck of a lot easier with the problems we have here. So I have 1 foot, and then you need an equivalence, correct? And 1 foot is 5,280. I didn't say that right. I wanted to say 5,280 feet is 1 mile. And I put it in the wrong spot. 1 mile. And then what? Because I wanted feet at the end. Then I have 6.5 miles. And it tells you you're going to do what? Multiply 6.5 times 5,280 feet. A heck of a lot easier than the last problem. So you have to multiply this, and I'm not going to carry that part through right now. But the point is straightforward. Let's go back to number 8 in the document cam, where we're going from feet to inches. The only thing that gets a little bit different here is 648 square inches going to square feet. So that's a little different wrinkle. So this is number 20. And I have 648 inches squared, and I want it to go to feet squared. Okay. Your equivalences again, right? So what do you know about a square foot? It's 12 inches by 12 inches, which is 144 square inches, right? So I can go, because I want this in feet, so I put 1 foot squared. I know from my table of equivalences it's 144 inches squared, and I'm multiplying by 648 inches squared. My inches squared cancel, and I just divide 144 into 648. We're okay still? Well, if I multiplied here by 4, I think I have 576. So if I divide, I'm going to have a little bit more than 4. Okay, 14. We have in number 14, 15 2/3 yards, and I want it to go to what? To feet. What do I know about that? I want feet in the top. So I have 1 foot is how many, or not 1 foot, I guess I need 3 feet there. I keep wanting to put a 1 on the top. 3 feet is 1 yard. And I have 15 2/3 yards. The yards cancel and multiply. Now it's up to you whether you want to treat that 15 2/3 as a decimal. I hope not. And instead, what would you do? Go to an improper fraction, which is 47/3. And your answer is 47 feet. Okay? Which is, if you'll go back to the fraction, a lot faster. Okay? Now, coming back center. First problems in this part right here were with feet, yards, etc. We play the same game up here, let's see, in terms of number 6. hours and minutes, days, years. Okay, these are just equivalences, correct? Now they're called relations in this text, but they are equivalences. 1 minute, 60 seconds. 1 hour, 60 minutes. Shouldn't be a problem there. If I come back to number 5, just scrolling across, cups, gallons. Okay, so your gallon is what? 4 quarts. Now, the quart is going to be what? 2 pints. And your cup is 8 ounces, and you can fill those in. So nothing particularly new there. As I come off that set, down here at the bottom, using some of those same ideas, we have pints to cups, gallons to quarts, same argument. So nothing particularly new there. So I come off that and go to the page 535. Again, some of these are a little bit more cumbersome. I think you can see 7 days to seconds is going to get rather messy because you're going to have a lot of 60s involved. 30 days to years, you're going to have to make some agreement in how many days in a year. 8.5 hours to minutes, probably best to write that as 17/2. But are any of those bothering you as you look at them? Just of the 4 that are up there. Which one now? Okay, I asked for the 4 that were up there, and you went to a different one. Okay, where's 55? I need to find it. There we go. 0.2 hours to seconds. Okay, you want seconds, right? So let's see if I can lay that against there and have it hold. Okay, yeah, we're going to have to go to the side. 0.2 hours to seconds. And I assume that the only thing that's bugging you there is the 0.2. I hope that's all that's bothering you. Okay, so I'm going to do that part, and to do that, I want seconds at the end, correct? So I'm going to have 60 seconds, and that will be, now you question, what's most obvious, I hope? 1 minute. And then the 1 minute would be in terms of, I don't want the ones, 60 minutes for 1 hour. Getting hung up in those ones. And then I have what here? 0.2 hours. Okay, now if you have 0.2, you could leave it that way. Or what could you do? You have 60 times 60. And what is 1/5? Thank you. And this will be in terms of seconds. So these are over 1. So the 5 goes into 12, and you have 60 times 12, which is 720 seconds, and you're done. So the idea, trying to go ahead and do what? Use a fraction to your advantage. Okay. Now, there's one more that we did that's very related to the kind of thing that we see in this section 7.3. How many feet per second if you're going 60 miles per hour? How do you set it up? It's 60 miles per hour, and I want it in feet per second. What are you going to do? This is miles. Okay, what? Feet per second, right? So if I start with feet and have what in the relationship as I start with feet? Pardon? Okay, the 5,280 feet. So 5,280 feet. No, it's over 1 mile. And then I can do what? The 60 miles over the 1 hour. Now what? I managed to get rid of miles, and I have feet per hour. So 1 hour, 60 minutes, That goes out. But I wanted seconds, so I'm going to have 1 minute, 60 seconds. And now I have feet over seconds, and I basically am done. So the 5,280 times 60 times 1 times 1 over 1 times 1 times 60 times 60. This will be in terms of feet over seconds. Okay, so the 60s cancel there. The 6, the there will cancel, giving me 528 over 6, and that ends up 88 feet per second. Again, the fractions being the best way you can do it. Okay? Any question there? Okay, let's go back to the document cam for a moment. I divided, okay, coming back to here, I divided 10 into here and 10 into here. 10 into 60 goes 6, 10 in here goes 528. So I just divided by 10. Okay, back to the document cam. Okay, that brings us down to the kind of problems that are at the bottom of page 535. And the kind of problem I just did is the escape velocity number 67. This is the escape velocity for Earth is 36,800, no, I didn't say that right, 36,687.6 feet per second. Calculate this as miles per hour. Just reverse of what we just did. Okay? So the problem we did in Math 10, that was a DMV problem we talked about, is what you do in the bottom of 535. The rest of those problems, I think you should be able to do. Section 7.3. Any questions about them or dimensional analysis? And again, I would encourage as much as you can, go to fractions and avoid the decimals. I've tried to select the problems in such a way that I don't think you're going to have trouble in the process. So if we're okay there, are there questions in 7.2 you wanted to ask about today? From 7.2 now. Okay, James, 7.2. $15. Oh, hold it. 15 from the computer, not from, okay. Can you tell me a problem like it in the book so I can put something in the document cam for people to see? Number 6? Example 6. Okay, just a minute. Or like number 49? Okay, just a minute. Okay, which is like number 49. Yeah. Which is what Emily was saying. Now in this case, I want the, let's see, I'm trying to figure out what I'm supposed to find here. Find the unknown length in the similar figures. So I come over here to something that's similar to it. Okay, A and B and C. So before I do that, let me talk about similarity with the triangle. So what first I'm going to do is draw a shape that's triangular and look at two triangles, and this is, I'm going to do 49 eventually. I'd like to start by looking at triangles. Okay, so this is where we talked at the beginning, just to get this idea of similarity. So these two triangles were similar. Reason, we had a 3, 4, 5, and all we did was multiply each by 2, and it gave you a new Pythagorean triple. Works the same way. 3 squared added to 4 squared was 5 squared. 6 squared and 60, and 8 squared, which will give you 36 and 64, will be 10 squared. What we argue is that if these two triangles have the same angles, So 90 degree and 90 degree, and this angle here is equal to that angle. This angle here is equal to this angle. Then if that's the case, we argue that these are similar triangles, and we say that there are proportional parts to these. That is, AB is to DE as BC is to EF. So any corresponding sides in ratio will be equal to the same ratio of the other corresponding sides. Now that's true for that triangle, which is a right triangle. In the same way, as we come off there and generalize those triangles, these are also similar triangles, but are no longer right triangles. But the argument works the same way. So in a sense, this was 18, we went to 24. What you're multiplying by appears to be, see if I can get that so it focuses a little bit better. This is 1.5 times, correct? Or is that correct? I'm thinking 1.5. I'm at 18 and going to 24. I was at 15 going to 20. So there I added in a third more. Here I'm adding in a third. So this is 4/3 times. So 4/3 times this gives you 24. 4/3 times this gives you 20. So the ratio is 4/3. So the argument is if each of these sides has been multiplied by 4/3, multiply by 4/3 here, and you get 28. Now I'm going to leave that there for a moment because I want to look at them as proportions first. So what I'm saying again is that 18 is to 24. Let me write this out first. Just with these two that work, as 15 is to 20. Okay, going to the board. In essence, when I multiplied 4/3 times this, I got this. So if I cross multiply, I should get the same answer, 360 and 360. Now that's what we mean by similar parts for similar triangles. So coming back to the diagram, we should then be able to say that 18 is to 24 as 21 is to the letter B, and play the same game as a proportion. Now you could say this ratio, in this case, I'm thinking of 4/3, so I could take 4/3 of 21 and immediately get there at 28. Or you can say 18B is 24 times 21, then divide both sides by 18, and if I do that, take 6 into here and get 4, take 6 into there and get 3, there's my 4/3. The 3 goes into here and into here, giving me, when I multiply those together, the 28 that we said is the answer. Okay? Now that works for these triangles. Okay, let's go back to the book. Now we're going to take that and go a step further into a trapezoid. So as I look at the diagram here, okay, bring that up. Let's see, can I still see that one side? No, let me bring that up a little bit higher. And I want you to see something from the diagram. I'm going to take two triangles. And I don't know how successful I'm going to be in making these look similar, but let's try it. Okay, there's the first. Here's my second. I'm going to try to run that just parallel over. And then in the same way, run this parallel, coming across. Now if I've drawn those so that this side is parallel to this side is parallel to this side, my argument is these angles, I'll do this A, B, C, and this I will run at D, E, and F, then angle A and angle D are the same. Angle B, angle E are the same. Angle C, angle F are the same. So these two are similar. Okay? Now, let's see if I can come down to there about 9. Now what have I created here? A trapezoid, correct? And if I run in a proportional way, this triangle happens to be that triangle, but I could run another trapezoid down here. So this would be like 2 trapezoids, and my argument is that they are also similar. So if I think, I'm not sure of how many letters I want to throw in here to mess you up, but I'm going to call this R, S, T, and B. Okay. ARS is also similar to this big triangle. And so if I look at parts of these triangles, I could argue by triangles that I have similarity. So to that extent, these 2 parts here are similar as these 2 parts are. And so I can, on basis of that, say that these are proportional in the same way the 2 sides are up here. We can play that game all the way through with similarity arguments, and we do that in a geometry course, and try to argue ultimately that the trapezoid RBCS is going to be similar to trapezoid TBCD. Now back to the diagram. That's what I'm seeing there. Just 2 versions of a trapezoid. And let's see if I can draw those and get them in some way about reasonable. And again, just coming over here, try to keep that parallel. And let's see, if I run this here, and then keeping it parallel about to here, I just get a smaller version of 2 trapezoids, essentially. I need to bring that down a little bit further, I think, to get what I want out of it. So let me see. About down to here would make more sense. And my argument is that these 2 trapezoids now should be similar to each other. So let's go back to the diagram on the numbers on that one, and I can't get close enough to a monitor. Is it 12 and a half?
12 and a half.
Okay, and 7 up here? And what's this side? 7. Okay, and 10 up here? Okay, for the other one? 4 here, 4.2 here, 4.2 here. And what? A in the top and C here. Have I got it now? And this is supposed to be B here. Okay. The numbers aren't very nice because of the 4.2. But the ratio is what? 0.6? So this is to this as a 0.6. 0.6 times this gives you here. Okay? And if these are similar, what must this be then? That's going to have to be 4.2 also. Now, in terms of what we have here, I could argue 7 is to 4.2 as what? 10 is to A by proportional parts. So if that's the case, then 7A is equal to 10 times 4.2, and you have to appreciate what the author did with the numbers, because the 10 times 4.2 will give you just 42. So 7A is 42, so A is 6. But the whole thing rests on the fact that this is, in essence, what? This is, as we slide over, the base of a triangle, okay, which, in terms of these 2 triangles, of similar triangles, they are proportional parts. Okay, now, what we haven't established that you would do out of geometry is that even though this part here is to the big part here, it's what's left that we're interested in. That is AT and AR are proportional to AB. Okay, they are the proportional parts. What we're looking at is RB and TB. So if the whole, this portion here is proportional to this, then what's left down here is also proportional. That's the wrinkle that's not established very well. But does that explain the idea, James, that you should be going through here? And then what would I do in this one? I again could say 7 is to 4.2, as 12.5 is to C, and solve it as a proportion. Is that enough? Okay? But again, if we were in a formal geometry class, we would take time to prove that these trapezoids are part of similar triangles and that all the things we're arguing here would hold true. Without that, it's sort of an act of faith. Any other question from 7-2? Sandra?
Yeah, it's called the tip of the computer and...
Okay. Most similar now? That's a good choice of words.
It's all fractions.
Can you give me the problem
I can't.
similar to it in the book? Which one?
It's an example on page 518.
Okay, I'll have to come back. 518.
31 in the book.
Okay, problem 31. Okay, so we have a proportion with a bunch of fractions in it, right? And your question is what to do with it when they have fractions like that? Okay, but, okay, keeping that on the screen, let's go to improper fractions. Okay, so you have 19 over 4 in the numerator of the first. It is over 11 halves, and we'll cut to the board momentarily. And that's equal to D over 33 halves. Correct? Now, what do you do when you get the problem like this? You cross multiply. Michael?
Could you write that as D over 1
No,
on the top part?
Oh, I see what you're saying, where you have D over 1 in the top, so it looks like an improper fraction also?
Yes.
I wouldn't object to that. What Michael's asking, can I do this? The answer is yes, if that would make it easier for you in multiplying. But what I would do, cross multiply and just rewrite it. Although, if I were doing it myself, I'd multiply both sides by 33 halves and then just simply try to reduce it that way. So again, I want this out from here, and if I just had the D over 1 on the right side, it'd be done. So if I multiply both sides by 33 halves, it'll save me some work. And then what do I hope I can do? That I can cancel something. Now, James, you were first.
So if you multiply it by 33 halves on both sides, right? You do the top and the bottom still, but like then what you
I'm just going to multiply this side by 33 halves and this side by 33 halves. So if I do that, I'm going to have 19 over 4. I'm going to invert and multiply, which is 2 11ths. And I multiply by 33 halves, and that's equal to D. 11s cancel. The 2 cancels. And it looks like I have 57 over 4. So this becomes 57 over 4, which, if you wish, is going to be 14 1/4. I by no means would want to take that and write it as what? A decimal. Does that answer your question?
I like that.
Okay. Well, my guess is they took this product and then they divided by this. So you're going to have 19 over 4 times 33 over 2 divided by 11 over 2, which becomes 2 over 11. Set everything else up before you do any canceling. Then do it all at once. Are we okay? Michael, you okay?
Yeah.
And most, I think, of what I'm seeing in quizzes and when you ask questions at times is not trying to find the least messy way of doing the problem. Least messy way. Kim?
Did you flip the 11 over 2 when you went to the bottom?
Okay, if I have 19 over 4 divided by 11 over 2, don't you invert and multiply?
Oh, you did.
Hence 2 11ths and multiply.
Okay.
Because you want to get D, you want to get D by itself.
Now, as I say, you could have just taken this product and divided both sides by 11 halves and end up with this. You'd have an intermediate step. I don't object to that. But think your way through rather than jumping in and just starting to do some calculations, because that's what I'm seeing in your work, where you're tending to do a lot of calculations and chewing up enormous amounts of time and maybe not doing the right numbers. Any other questions? 7-2. Now, comment for you. This problem is no different than what we did earlier without the mixed numbers. Okay? And so what's messing you up a little bit is the mixed numbers, which you go to improper fractions. But that's where if you benchmark, and as we come back to the problem in the book, the argument I would make is, okay, what would I do if instead of having, okay, looking at the problem now, take off all these fractions. So if I just had 4 over 5 and a 16 here, what would I do? So again, take off the fraction parts. So I have a 4 over 5 on the left and D over 16 on the right. I just cross multiply, and then cancel. Okay, so hopefully an easier problem gives you direction on a harder problem. Anything else in 7-2? Okay. Looking at the problems there, did you have a problem like this on the computer? I gave this one as 55 in the book, where you were trying to get distances across like a lake or something, or did they give it? They did give one like that. Were you okay in those? Okay, one of you likes it and the other says it's weird. As we look at this, we want the width of the Grand Canyon and consider the measurements shown to calculate the width of the Grand Canyon. And so the understanding is from here down to the other green belt is what? Is your Grand Canyon. And so what they did is take two triangles, and I don't know where I could draw that. That makes sense of it. Let me try it on the board. Let's, Debbie, bring that camera back over here on the right side over here, if you would, please. And just a comment to establish what we're talking about there. So if I do this, I need to have that back up there. So I'm going to draw a diagonal like this. I'm going to draw a line down here, and then do something like this, if I can get a right triangle there, and then another right triangle down here. Now that in essence is the diagram, is it not? Okay. Couple things. This is supposed to be 90 degrees here, 90 degrees here. Now in order to have similar triangles, you have to establish one other angle that's the same size here. Two lines that intersect create angles that are the same. So that diagram forces this triangle to be similar to this. So again, if I just take any two intersecting lines, doesn't matter how they're intersecting, these angles right here are referred to as vertical angles, and they will always be the same. And the fact that this was 90 and this was a 90 allowed you then to do what? To take two measurements you have here, and these are what? Not across the canyon. So these two sides must be proportional to these two sides. So if I can get, how do I want to do this? I'm going to put a star here. If I can get those two, that's easy enough to do along the edge of the canyon. And then just measure out a certain distance here, wherever these meet. Then this side, if I can find that, I can find this. That's the argument. Let's go back to the diagram. In terms of, wow, I can't see the letters in that. They don't give any letters on it, but you're basically saying 1.384, this value, let me bring it down tighter. This 1.3, or 1384 is to 1.2 as what? No. It's the long is to the short as the long is to this short down here. So what you should have set up was that if this is going to be x, x is to 10.4 as 1384 is to 1.2. And then just solve the proportion. Neat problem, worth remembering if you ever get lost at the Grand Canyon. Okay, you've got homework in 7.3 for today. We'll talk about that tomorrow. 7.4 is just metrics, same ideas. That'll be a little bit harder. And we'll continue answering questions. So Debbie.